Today, we're going to talk about drag, and we talked about drag a little bit last week because we talked about dimensional analysis and how that helps us figure out the drag on objects using a wind tunnel and a small model. But now we will talk about drag in more depth. Okay, so drag is the force a flowing fluid exerts on a body, on an object. Here we have parallel flow over a flat plate. And in this case, drag comes entirely from viscous shear stress. And we've talked about that before when we talked about viscosity, and we had the two plates, and one of the plates was moving and the other one was flat. And we said that viscous forces were dragging back on that moving plate. So this is the same thing. You have flow going past this flat plate. Their viscous forces on it will create drag. And the force would just be the shear stress times the area. Okay. This kind of drag is called friction drag. But there is another kind of drag which you would get. So here we took that same parallel plate or that same flat plate and we turned it perpendicular to the flow. So now instead of the fluid flowing along it and sort of the viscous forces dragging on it, what we get is a different kind of drag. So in this case, where do you think the drag comes from? Because now the flow isn't dragging along the surface. So where do we think the drag comes from?
Is it fluid on fluid?
Okay, well, it's a little bit more complicated than that. Where it comes from is the pressure. So before it came from the viscous forces, now it comes from the pressure. This whole part here, the reason that it looks all cloudy is because this is just sort of a turbulent area. We call this the wake, the turbulent wake. So the flow comes here, it hits there and stagnates, right? Just like we've talked about. And so you're going to have a high pressure area at the front and a low pressure area behind it. And the difference between the pressure creates the drag. So if it's high pressure here and then low pressure here, and so the net pressure force is going to push it, in this case, to the right that way.
Dr. Nickerson?
Will the fluid not produce any friction on the plate? It will a little bit, but in the case of this, the friction drag is going to be really small because the friction comes when it's rubbing alongside it. And here it does a little bit, but that drag will be small compared to the drag that comes from the pressure. Someone said my name. I wasn't sure who it was.
Yeah, it was me. The area, what area is that in that term? Is it the cross-sectional area of the plate or is it the area?
It's the area of the plate because again, think about pressure forces, right? So you have pressure on this side and pressure on this side, and you multiply those by the area of that wall or that plate in order to get the pressure force.
Okay, yeah, that makes sense.
And then I have a follow-up question as well.
Yes.
So where would the pressure be greater here? So I would guess that the pressure would be greater on the right side just because that would push it back that way, right? If it's higher pressure.
Yeah. So
is that correct? And is that just because it's turbulent?
High pressure on this side, low pressure on this side. Okay. And think about, okay, imagine you're carrying something like a shield in front of you in the wind, right? And you hold it up and it will blow you back, right? It will blow you in the direction of the wind. That is the drag, that is the pressure drag Okay. You can also call it form drag, but I mostly just call it pressure drag. So that is the pressure drag on you. So the pressure drag will push you back in the direction of the flow, and it happens because the pressure on the front side of what you're holding up will be higher than the pressure behind it. Does anyone want bicycling, like bicycling races? Zach, can you tell us what drafting is?
So drafting is when you're close enough behind someone else while cycling. And so it's the same example with the shield. So if you have someone with a shield, but you're behind them, the shield takes all the drag, and you're in the turbulent wake, so the low pressure area. So it's easier for you. You can go faster.
Yep, exactly. So that's why in bicycling races, people want to be behind some other guy, because that other guy is going to take the full brunt of the drag, and then the guy behind him will be in the low pressure area, which has less drag on it. And teams of bicyclists will swap out where they are, and they'll take turns being the guy in the front. That is pressure drag.
And then one more quick question as far as just the reasoning for the pressure difference. So I mean, it makes sense if you think of like the directions that it's going, but why is the turbulent area, why is that lower pressure? What is the connection between the turbulence and the low pressure?
All right. So two things. First of all, this front area, remember when we said that stagnation pressure will be, when it hits this, the velocity right where it hits this will be 0, right? And so then the pressure would be stagnation pressure, which is P plus 1/2 rho V squared. So first of all, the pressure on the front will be higher because it hits it, it stagnates, the pressure rises. And then over here, it is just flowing around, and you've got, we'll talk about that in a second. But part of the reason is just the velocity there will be high, right? So that will lower the pressure, but also just energy is lost by all of the turbulence swirling around that's in there. Okay. This comes down to what's called flow separation. Okay. So you have this flow, it's coming towards this body. We would call this a left body, and the flow goes around here and it separates. And that's what causes this turbulent wake in here, because the flow on either side is separated from itself. And so you got the turbulent wake. So that's another reason, is the energy and that flow mostly went into the parts that are continuing to go forward. And you're just left with this that's left behind, okay? So wakes form when flow separates behind an object, usually low pressure, usually turbulent. Right. Here's a question. What kind of drag, friction or pressure, explains why a marble drops more slowly through syrup than through vegetable oil?
I would guess friction drag because it has the shear stress as one of the coefficients in the equation.
Okay. Yes, KK, you are right. Have you actually done problems with ball drop viscosity problems before? Well, the reason a ball drops more slowly through syrup is because the syrup is more viscous, okay? And if it has, it's the friction drag that has to do with viscosity. More viscous things give more friction drag. Okay? So this, in this case, this would be friction drag, and it happens because you're dropping it in, so it falls slowly and viscosity is high. You'll get a very low Reynolds number. You'll get friction drag will be dominant. Most of the time, as I said, that delta When you have a situation like this, delta P will be a lot larger than that shear stress. So which kind of drag is usually more significant?
Pressure drag.
Pressure drag. Okay. So do you think friction drag is more likely to be significant in laminar or turbulent flow? And this time, don't answer out loud, I have a poll. Okay. Which is okay. 48. All right. So 71% of you say laminar and 29% say turbulent. The 71% are right. Friction drag is more significant in laminar flow. Does someone want to explain to me why that would be?
I could try that.
All right.
So laminar flow is a lower Reynolds number.
Lower
And then if you think about the bottom of the Reynolds number is viscosity. So when I'm increasing the viscosity, then I'm decreasing the Reynolds number and I'm getting therefore more laminar.
Yep.
And therefore like more laminar would mean that the friction is going to play a bigger role because I'm also more viscous, or at least that ratio.
Yes. More laminar means more viscous relatively. It also means, and so that makes friction more significant. It also means slower. And the higher your velocity is, the bigger the pressure difference you get, right? Because we said it hits the flowing fluid hits the front of the object, which creates more pressure the faster it's going. And then of course the difference between that front and the back where the air is still low velocity will be bigger the higher the velocity is. So higher velocity, more pressure drag, higher viscosity, more friction drag. So in laminar flow, which is lower viscosity, higher viscosity and lower velocity, you get more friction drag. But laminar flow we've talked about is relatively rare. Most of life is turbulent. Okay. Now let's talk about lift. Lift is the component of those same forces, the pressure forces and the shear forces around an object that are normal to the flow. Okay, so your net force from pressure in this little wing I've shown you is sort of at an angle like this, and you can split it into parallel to the flow, that's drag, and normal to the flow, that's lift. So there actually isn't a fundamental difference between drag and lift. They come from the same fundamental forces. All that changes is which direction they're acting on. So that means what's important for creating lift is the angle of attack. So that means we have these three sort of wing shapes that are at different angles compared to the flow. And in the first one, you can see how you tilt it will change the relative size of the lift forces and the drag forces. Now, this should make sense to us. I want you to imagine that you are driving in a car. You're in the passenger seat, right? The window is open, you stick your hand out, and then you go like this. So when you're doing that, your hand is out the window of the car. When your hand is like this, what do you feel on your hand?
Lift.
Yes, you feel it pushing your hand up. And when you do like this, what do you feel? Feel it pushing it down. Okay, so the only difference then is the angle of attack. And that's why you do this when you stick your hand out of the core. When you change the angle of your hand, you change how much force there is pushing you up or down. Okay, so things like airplane wings are designed in order to maximize the lift and minimize the drag by just their shape and their angle. Okay.
Dr. Halverson, sorry, Nickerson, sorry. Just looking at the first drawing there, I'm trying to figure out the lines that are running across the page. Is that the direction of the
Yes, that's the
flow?
direction of the flow. So those are called streamlines.
And so I'm trying to see how that first one has, the top one has any lift, because it seems like it's all flowing.
It has a small amount of lift, probably because you see here's the turbulent wake. It's sort of curved like this. There's probably like a net force kind of this direction. Very, very small amount.
Okay, so maybe it's just like the arrow, the size of the arrows are what's throwing me off, because it looks like that one has more lift than the one that's angled on the bottom.
Well, I suppose, see this one, it's got more of this wake here, so there's going to be a bigger drag that way compared to the lift force. Okay. But there's also that friction drag all along here, right? Which is just going to have, because of the way this is tilted, that friction drag is going to have the effect of lifting it up a little. Just like, ooh. Okay, so why do airplane wings have retractable flaps? If you've had a seat near the wing in an airplane and you look out, you should see that these little flaps are up during takeoff and then they flatten out. Why do they have those?
To increase the drag.
To decrease the drag and increase lift. But the reason they're retractable is that when you're launching, during takeoff, the airplane and the wing is at a different angle than when you're in the sky. So when you're in the sky, you're like this, or I don't know exactly. You're at some angle when you're in the sky, and then when you're taking off, you're at a different angle. And so then they have these little flaps so they can adjust the angle of attack during the takeoff part and the landing part in order to maximize the lift.
So when they want to go back down, do they have to have like another set of flaps on the bottom? Do you know?
I do not know. Presumably
Okay.
they do something different when they're going down, but
Yeah.
you
'cause I'm
still
like,
want lift
oh.
happening when you're going down, or else you'll go down too fast. So I don't know.
Yeah. Yeah. Okay.
Yeah, I don't know that. I do know though, what must a stunt plane be able to do in order to fly upside down?
Adjust the wings.
Yes. Yeah. Christian, is that how you pronounce your name? Sorry.
Yes.
Christian. Yeah. They have to be able to adjust the wings somehow, or because you want to be able to change the shape and the angle of attack, keep the lift up going. Okay. This also, so that's how lift works. We won't be doing a lot of problems with lift. We're mostly going to be talking about drag, but that's where it comes from. Now let's talk about streamlining. So you have heard the word streamlining before, right? And you can look at all of these things. There's a couple of cars, a train. You can see that these things look streamlined, or you should. So what does that mean to you when you hear that something is streamlined?
Aerodynamic.
It's aerodynamic. Okay, and what does that mean?
Air flows very easily around it.
Air flows very easily around it. It is designed in such a way to reduce drag. So why though? So you can sort of see they all kind of have the same look, kind of like snaky almost. So why does this streamlined look, reduce drag and make things more aerodynamic? We shall see. Okay. Is there any, this I just thought was funny. I was searching for images of streamlined things and I found this iron. Is there any reason to streamline an iron? No.
It makes you faster in Monopoly.
Yes. You would have to be ironing extremely fast in order for pressure drag to be important. Anyway, but so now when people say streamlined, a lot of time they just mean kind of looking sinuous with the smooth lines like this. Okay, but here's a thought. Which of these cars do you think experiences more friction drag?
Is it the streamlined one?
Probably the streamlined one, right? Because it's closer to being, a flat plate and the flow will go over it. So then why does streamlining decrease drag?
Would that be because there isn't the flow separation? So
Because
then you
it
don't
isn't
get
the
that
flow
difference
separation.
of pressure?
Streamlining reduces the pressure drag by reducing flow separation. And you can see that here. So that's what the streamlining does, is it reduces flow separation, it reduces that wake, and therefore reduces pressure drag.
Is that how bikers are able to get behind like a semi and just kind of get pulled with them?
Yeah. Oh, yes. The same thing we were, well, that's kind of a drafting thing like we were talking about before. The semi is going to have a huge low pressure area behind it. And so if they're in the low pressure area, then there will be less pressure drag on them because there's going to be less pressure in front of them. Okay? The streamlining is about, so again, these are called streamlines. If you just sort of follow the line of the flow, that's what. And so streamlining reduces the separation of the streamlines. That's why it's streamlining. So you have less of a wake behind there and less pressure drag. So it said behind a semi-truck is just a big square. It's not streamlined at all. So there's this huge low pressure area behind it. So bikers, do motorcyclists, do they try to get behind semis? I didn't know that. But if they do, it would be lower pressure there and it would be less drag. It would probably increase their gas mileage for motorcyclists to stick behind a semi.
With the friction drag, is that just all about, so like the streamlined one, is it more fluid touches the surface, so there's more
fluid
friction?
touches the surface. It's got more of a flat surface that the fluid goes along. So it's not so much the fluid touching the surface as the flow, the direction of flow touching the surface. So this will have more friction drag, the streamlined one will. But remember we said that friction drag is usually small compared to pressure drag. So the trade-off is usually worth it.
So Dr. Nixon, if the streams meet up, does that mean there's no pressure drag?
So yes, that is what that would mean. In real life, if you have a car or something, there's going to be some pressure drag. They're probably not going to meet up perfectly in something that's going really fast and can't be designed as a perfect teardrop like a car or something. But yes, if they meet up like this, there's no wake at all. That would be no pressure drag.
So would that be on like the top of the tier? Is there still some pressure difference from like stagnation pressure?
Yeah, there might be some. So I suppose there would be maybe a small amount just from the stagnation pressure right there. So maybe a little bit. So that leads us to our next polling question, which is, do you think it makes sense to streamline an object in very low Reynolds numbers flow? Very low. Okay. All right, so 91% of you say no, and you are right, because in very, very low Reynolds number flow, we don't get this flow separation anyway, because that really slow viscous flow is just kind of going to wrap around the object. And so streamlining it would likely not decrease your drag very much. And instead, you should focus on making it smoother, for example, so there's less friction. That is what you would do if you were trying to minimize drag in a very, very low Reynolds number flow. Tyler, you have a question.
Yeah. So for the streamlined shape, like just like my intuition, like wants it to like reverse the other direction for the flow.
Reverse the other direction? I'm not
So
sure.
like if it was a car, the car shape looked like the teardrop should be facing the other way. Does that make sense? Like the
Like this?
yeah, like that.
Okay, well, the car also has things where you want the window and you want the engine to be somewhere. So this is the ideal streamlined shape where the bulbous part is in front and then there's like a tapering tail right there. But cars have other considerations as well, where it's got to be kind of car shaped.
Dr. Nickerson, in addition, I know a lot of the race cars, they actually will create the aerodynamics such that it creates downward force on the car as well to help with friction coefficients on the road.
Yes.
So there's more than just streamline consideration.
Well, and also those little, I forget what they're called, the little flappy thing on the back of the
spoiler,
on the race car.
Spoilers.
The spoiler, yeah, what that does is that it creates, well, lift, but it's not lifting up, it's pushing down. So the spoiler is angled in such a way that it pushes it down, which helps with holds the car down, right? Which helps in some way I'm not sure about because I don't know about race cars, but that is what a spoiler on a race car does. So
My
yes.
guess would be that getting lower to the ground, there's less issues with the air underneath the car. Aerodynamics would be helped that way.
Okay, that would make sense, right? So the more you push into the ground, usually the more friction you have, right? Like if you have a box and you push it into the ground, it creates more friction. But I don't know how that works with wheels because wheels need friction anyway. But if the teardrop shape was like this, so it was kind of reversed, then the flow would go this way and it would separate here and you would get turbulent wave. So that's why teardrops that way. Okay. So streamlining mitigates flow separation. That's what streamlining does. So a non-streamlined shape, you can also call it a bluff body. So you hear something called a bluff body. That also means something that's not streamlined. It's just a chunk of a thing and will create a big wake behind it, like a semi-truck, which is just a big square. Let's go back to drag coefficients. We talked about drag coefficients before. The form of the drag coefficient we used when we were doing the dimensional analysis, it didn't have that 1/2. This is probably the more common form of the drag coefficient you'll see. So the area there, A, is the projected area of the object. And the way you can think about it is, you should remember this as the stagnation pressure, or at least it's the kinetic energy part of this stagnation pressure. So you have that kinetic energy pressure or the stagnation pressure, multiply it by A, you get a force. You get the pressure force pushing on it. More or less, you get the general scale of it. So that's why that 1/2 is there. Yeah, so we write that down. Now, how do we figure out what the friction coefficient is? Again, we talked about how you can do it using dimensional analysis and with models and wind tunnels, but, well, can also rearrange the drag force like so. This becomes the equation for drag force. Now remember, we said from that dimensional analysis, we said there were two pi's, and the pi's were the drag coefficient and the Reynolds number. And we said the drag coefficient is some function of the Reynolds number, but we don't know what that function was. And the nice thing about the models is it allowed us to do analysis without knowing what that function was. But you could also just do a bunch of experiments at a bunch of different Reynolds numbers and get yourself experimentally the function for drag coefficient as a function of Reynolds number. Like so. So this, for example, is for a flat disk. You're going to get a different relationship for every shape. Again, this is one of the reasons why a lot of times you take cars and you do the wind tunnel experiment instead of trying to figure out what the exact equation for that exact shape of car would be. Yes, so drag coefficient, some function of Reynolds number, you can plot it experimentally. You should also see that eventually it starts to level out. So for most shapes, drag coefficient is about constant after Reynolds number 10 to the 4. So for a lot of common shapes, we have published the function of Reynolds number, right, where you can plug it in and it's a big complicated equation and it would get you what it is all along here. But after Reynolds number about 10 to the 4 comes about constant, and that is most of the time Reynolds numbers are high. A lot of the time that we care about they are. So that means that we can just sort of take a lot of times you can say the drag coefficient for this shape is 2.6. And if the Reynolds number is high enough, you can just use that. There is a table in your book, which I also made a copy of and posted to Learning Suite under the lecture slides for this lecture that gives you drag coefficient for different shapes.
Dr. Nickerson?
Yes.
You know off the top of your head what velocity that corresponds to in air at a 10?
It does not. Okay. So off the top of my head, remember, it doesn't correspond to any velocity because Reynolds number, rho v d over mu. So the density of air will change a little bit depending on the temperature. The viscosity a little bit too, but not as much. Then there's v, and then there's d, which is the size of your thing. So if your object is really small, then it can go faster, or it would have to be faster.
Yeah, it's not only a velocity thing, it's a size and shape thing. Got it.
Well, it's the size, the shape, and the velocity. They're all those things together, which is the point of having some parameter like the Reynolds number that kind of puts it all together for you.
Yeah, okay.
Okay. So that area that we talked about, that's the frontal area, and I want to show what that means. So for example, here I have a cylinder, it's on its side, so the flow is going this way. What would the projected frontal area of that cylinder be? Frontal area, the area facing the flow.
That would just be pi r squared, right?
Pi r squared. I always do things in terms of diameter because we're in fluid mechanics and you have pipes and those are always diameter. But yeah, pi r squared, pi to the fourth b, not to the fourth, squared. But now let's, okay, now turn the cylinder on its side. Now what's the projected area?
A rectangle?
Connor, what did you say?
A rectangle?
A rectangle. The projected area is a rectangle. Okay, so if this is height. And this is diameter. What would the area of that rectangle be?
H
HW.
times D.
The
Or
height
D.
times the diameter. So that's what we mean by the projected frontal area. Let's say you had a parachute, and the parachute has a round parachute like that. Here's the person. Then the projected area would be the area of this parachute like that, because guy's flowing down. This is the direction of the flow. Okay. Tyler, your little yellow hand is up.
Sorry, I might have just left my hand up on accident.
All right, so Ryan then?
Yeah, so just to make sure I understand, with frontal areas, we're just looking at the 2D version of that front part?
Yep, it is the 2D version of the front part, the projection. You have a three-dimensional object, so the 2D version is called the projection. And it's a projection going in that direction of the flow. All right, so we have a problem. Circular sign has a diameter of 50 centimeters and is subjected to normal winds up to 150 kilometers per hour at 10 C and 100 kilopascals. So it's a little cold. Determine the drag force acting on the sign. The first thing I would do in here, I'm going to assume turbulent flow just because 150 kilometers per hour is really fast. So I'm going to assume turbulent flow. If I didn't want to assume it, what I would do is I would look up the viscosity of air at 10 degrees C, and I would find the density of air. And then I would find the Reynolds number. And what diameter or what D would I use for the Reynolds number?
The 50 centimeters?
The 50 centimeters. And I would find what the Reynolds number was. And if it was big enough, then I would assume I could just use the turbulent drag coefficient. All right. I'm also going to, as it is, I'm just going to assume turbulent flow. I still need the density. So I just used the ideal gas law to get the density. This temperature, it's slightly higher than it would be at like 20 C. All right, so what do you do next?
Don't we need to find the delta pressure for the sign?
Okay, so we could do that, but that would be hard, right? The whole point of this is that we can take a shortcut and we can just use force drag equals 1/2 rho v squared a, or times, got the most important part, 1/2 CD rho v squared a. That's the point of the drag coefficient. The drag coefficient takes all of the pressure where you would have to figure out the pressure on the front and the back and integrate over it, and who knows what else would happen, and just uses this drag coefficient we found experimentally. So let's find the drag coefficient. So I will look at that table, as I said, that's in the book, and I put it on Learning Suite for you. Like, here we go. This table, this is just part of it. And that sign, what shape is that sign like, most like on this page?
Circular disc.
This thin circular disc. So I'm going to take the drag coefficient to be 1.1, which I can do because I'm assuming turbulent flow. So it's Reynolds number greater than about 10 to the 4th. So that's what we're assuming is turbulent for these purposes. Some of them, it may say something a little bit different. Okay. So now, times the area. Kilometers per hour, which times 1,000 meters per kilometer times 1 hour per 60 seconds squared times the area, which will be pi over 4, 0.5 meters.
And then quick thing there, I think that it would be the 1 hour over 3,600 seconds.
Oh yeah, yep, you are correct. Because it's not minute, it's not a minute, it's an hour. And you should get, has someone plugged this in for me?
I got 5.54 newtons.
5.54 newtons. Did other people get that? Can I get a second? Okay. So if you plug everything in right, you should get the right answer then. And that is what the drag coefficient allows us to do. Now, with our last few minutes of class, we're going to talk about flow over a flat plate. So in a flat plate like this, most of the flow now is going to come from friction drag instead of pressure drag, because we've got all of those viscous forces going along the surface, dragging it, and the turbulent wake is very small. So now most of the drag is going to come from friction drag. And so we now say, instead of the regular drag coefficient, we're going to call it the friction coefficient. So it's just sort of defined the same. It's the friction coefficient now. Define this. Okay. So when we're talking about flow over a flat plate, we need to discuss the concept of a boundary area. So around some surface, there's going to be an area where the viscous forces are significant. Remember, we said the farther you go out, the less significant it will be. So the area around the surface, we call that the boundary layer. For parallel flow over a flat plate, the boundary layer looks like this. Okay, for the last question, Zach says he's getting something higher. As I said, just if you plug it in right and double check everything, it should come out right. Okay, parallel flow over a flat plate, boundary layer looks like this. A few things you should notice. It gets wider as it goes along. It starts out as laminar at here, and then at some point, it starts to get more turbulent, and then from there on out, it's turbulent. So, given that what this is, do you think the Reynolds number is constant over the whole plate? No, Connor is shaking his head. Why do you think not, Connor?
Because the flow is changing from laminar to turbulent, which probably would lead to a change in the Reynolds number somehow.
Yeah, the flow is changing from laminar to turbulent, and you know that the Reynolds number is supposed to tell you whether it's laminar or turbulent. So if it changes, it has to change. And the same thing then for the friction coefficient, right? Because remember, the friction coefficient or the drag coefficient are functions of the Reynolds number. So if the Reynolds number is changing, the friction coefficient is changing. Okay, like this. The friction coefficient as a function of x. So as you go farther along the plate, it changes. And that's just going to be the instantaneous friction coefficient at any point. But that is not that useful to us because we want the force over the whole thing, which we could get by integrating over the whole thing. That's how you would do it. So this is what it would be for x. Don't write this down though, because we are going to, you integrate it over this and you get an overall Reynolds number and an average friction coefficient. All right, so these are just experimental relationships. You can integrate those instantaneous friction coefficients, you get this one. There's a different one for laminar flow or turbulent flow. So what you would do if you were solving a problem with flow over a flat plate is first you would find the overall Reynolds number. And if it's greater than about 5 times 10 to the 5th, then you usually assume is turbulent. So that assumption means there's a laminar part at the beginning and then a turbulent part. So it kind of has to be long enough that the laminar part is just small and it becomes insignificant compared to the turbulent part. So sometimes it'll be in between and things get more complicated. But if it's long enough and the Reynolds number is big enough, we assume it's turbulent over the whole thing. L is length. So L is just the length of the whole plate. Problem, so air at 20 C in 1 atmosphere blows at 10 meters per second over a smooth flat plate that is 5 meters long and 0.5 meters wide. Find the drag force on the plate. I use 20 C on purpose because the properties, the density and viscosity of air at 20 C are just in the table in the back or front of your book, depending on the edition. So what do we do first?
Do we check the Reynolds number?
Yep, we get the Reynolds number. So we just do the Reynolds number. Rho VL over mu. This is the overall Reynolds number for the whole plate. Also notice this density is a little bit less than the density we did for the 10C air. And that should make sense because the colder a gas is, the more dense it will be. Just wanted to point that out. But cubed over times 10 meters per second times 5 meters over 1.825 times 10 to the negative 5 kilogram meter per second. I got 3.3 times 10 to the 6th. That is what I got, assuming I plugged everything in right. But point is, it's about 10 to the 6th. It is well over 10 to the 5th. I'm going to assume this is just turbulent flow, that the laminar region is insignificant, and we can just use the turbulent friction coefficient. Yeah, REL is kind of an average value or sort of an overall value for the whole plate. Okay, so did that. And so then the friction coefficient is equal to 0.074 over Reynolds number to the 1/5, which comes out to, someone tell me what, someone plug it in and tell me what you get.
Is that an 074 or an 034 up top?
That's 0.074. Yeah, 0.074.
I got an 0.003677 or
.003677.
Yep.
Me too.
0.003677. And so the drag force in this case, sort of because the force from friction will be most of the drag force here. So we can use 1/2 CF V squared A, or not A, sorry. Well, it is A, but now it's the area of the top of the plate. So now it's not the frontal area, it's the area of the top of the plate. So we have 1/2 .003677 10 meters per second squared times 5 meters times 0.5 meters. So that's the area of the top of the plate that's in contact with the fluid as it's flowing along it, creating friction. That gives us our drag there.
Does drag force not also include density?
It does. You are correct. That would be 1.204 kilograms per meter cubed. Right there.
Dr. Nicholson,
Yes.
will we have to do anything where we're determining because this is just like where there is no like pressure difference, right?
Yes, so this is where, so this is specifically for parallel flow over a flat plate, because in this specific instance,
right.
This is a specific setup where we know that the pressure drag is going to be really small and the friction drag is going to be big because of parallel flow over a flat plate. This is what this situation is.
If we have an instance where it's like angled and we have both, will we have to find both pressure and?
So if it's, I don't know whether we give you the resources for any, like I wouldn't ask you for anything where I didn't give you what the coefficient should be. For, depending on the angle a little bit, there's going to be some pressure drag and some force drag. And then the more you do it, pressure drag is going to get bigger and bigger and bigger and bigger. So we do not teach you anything about all of those ambiguous area. We're talking about this parallel plate specifically because it's an example where it's kind of simple and it's just the friction drag. So you can learn about that. And then most of life, we're just going to assume it's pretty much all pressure drag. So the drag coefficients that you get like on this table, they actually include a little bit of friction drag in them. So there will be a little bit of friction drag contributing to the drag force around these objects. This experimental drag coefficient that we have, it'll just cover them both.
Dr. Nickerson, I had a question.
Yep.
So, like for the boundary area for a cylinder, would it be the surface area of like that, you know, the side, I guess,
Okay,
like
well, a boundary area over a cylinder, it will depend on what's happening. So if you had, let's say you had a nice fat cylinder like this, like so, and it's kind of long, so there will be pretty fat wake, and then we'll have this drag right there, and it's like that. Okay, so there will be, and let's say it's on all sides, like so. So like it's a pipe and there's flow all around it. Okay, so in that case, the area that friction drag, the area for friction drag would be the surface area all around the sides of the cylinder, right? Because that's where it's flowing along. And then the area for the form drag or for the pressure drag would be this cross-sectional area here. So that would be pressure drag area. And this would be friction drag area. But again, in most cases, the pressure drag will be really big, and you would just use this. But I know if you had a long enough cylinder and it was thin enough, if you had a long enough, thin enough cylinder, probably the friction drag would become more significant, and you would have to use some other relationship, which you could probably find somewhere. I'm sure someone's published a paper on that, but.
Okay, thank you.
And then Dr. Nickerson, back to that flat plate example. Does the coefficient account for the fact that there's friction along the top and the bottom, or do we have to double our area?
Okay, so that, yeah, so I suppose I didn't say this in the problem, but I was assuming the flow was only on one side. If it was on both sides, then yes, you'd have to double the area.
Okay, cool. That makes sense then.
Yeah.
And then maybe could
That
you,
velocity is squared there.
do you mind explaining this boundary image, like the boundary diagram where it explains the multiple regions of flow? Can you explain what those like green chunks are? Or are those just kind of like,
those green chunks are showing the velocity profile.
okay, it's
Yeah.
almost like a zoom in at that specific point, I guess.
Sort of.
But like,
it's just over here, it's showing. So remember we said that for turbulent flow, even though the velocity is actually swirling around, you can kind of average it out and get an overall velocity profile. So that's sort of what it's showing, is what that kind of averaged out velocity profile looks like.
okay, that makes sense. And so streamlines are different than the velocity profile?
Yes, yes. Streamlines are different than the velocity profile. So in laminar flow, it will end up being, well, the streamlines don't show the velocity at all. The streamlines just sort of show where the fluid goes.
Okay, so they're less like quantitative, I guess. They're more just qualitative.
Yes, and most of the time, you can calculate a streamline from the Navier-Stokes equation and things. But another way to do a streamline is you have a little thing that makes bubbles. So you have some water and it's flowing along, and then you stick a little stick into it or something, and which creates bubbles, and the bubbles are white. And so those white bubbles will move along and create a streamline. They did this, you can find educational videos that are black and white from like the 40s that show people doing this. So this allows you to show sort of the path of the flow and what it looks like. That's what a streamline is. It just shows the path of, like if you took a little piece of fluid and followed it around, that's what it is. Doesn't have any, it doesn't show what the velocity is.
Right, okay, cool. Thanks, Professor.
Cool.
Thank you.
All right.
Could you go to the next slide really fast? Oh, okay.
Oh, yeah, sure. I'll go back.
I think my calculations are off, so I'm just trying to see.
This one or
One more. Yeah, with the.
That one?
No, where you had the full calculation out.
Oh, the problem.
Yeah. Okay, appreciate it.
All right, so what did you think you got off?
I actually don't know. I have no idea. Oh, I didn't multiply by 5. Okay, never mind. I just forgot. I multiplied by 0.5, but not 5 for the.
Cool.
Yeah. All right, thank you.
Thank you.